Welcome to this review on applications of our differential equations. And I'm focusing on two parts, the mechanics, which is 4.3 if I'm not mistaken, harmonic motion is chapter 6. We also did cooling and mixing but I'm not going to review those, okay? So I'll stick to these these problems here. And so let's start with the mechanics, and this is often, not always, right? The situation is we are somewhere and we either launching something or we dropping something, and so this is y then. On Earth, then we have a certain constant here. Now assume that we are on a planet. It's a slightly smaller planet than Earth, where g is equal to 6 meters per second square. And Earth is 9.8, so this is a smaller planet. I don't know exactly, perhaps Venus or something like that. And suppose that the atmospheric resistance is proportional to the velocity squared. And in fact, the resistance force is 48 Newton when the velocity is 2 meters per second. Okay, so now an object weighing 12 kilogram 12 kilogram, and did I write, what else did I have? Sorry, I'm looking for my notes here. I thought I wrote it up somewhere. I guess I didn't. Yeah, an object weighing 12 kilogram is launched from the surface, say, with a speed of where was the speed here? I'm sorry. Speed of 0.6 kilometer per second. Okay, so we are somewhere on the surface, or so. It doesn't really matter where exactly we are, because this is a problem on velocity, so not so much on position. And so for simplicity, let's just launch it from here, right? So this object, this rocket or whatever, let's make it a rocket, is launched with a speed of 0.6 kilometer per second. Okay. So our mode of movement is upwards. Okay, it's always good to know whether we are dealing with upwards or negative. So the speed here is a positive constant here. So that's sometimes I saw people interpreting this wrong. If you go upwards, then your velocity has positive. If you go downwards, then your velocity is negative. Okay. So even if you launch it here, eventually it will go down, sure. But at the moment of launch, it's going up. That's what matters. At the moment of the launch, is it going up or is it going down? Okay. So, but coming back now. So this is the setup. Okay. First of all, what do we need? We know that the equation is MA equals minus mg minus, so now we have to think about it. What is this? Since we are going up, the resistance is also positive, right? Because the air will make us resist going up. So we have here plus kv square. Okay, so that's the equation that we have to deal with. Now we have to find out what all these constants are. First of all, what is m? Let's start with that. So we know that the weight is mg. And we know that g is given to be 6, right? So it's 6m. And the weight, they told us, was 12 kilo. So we know that m is 2 kilogram. So m is 2 kilogram. Let's not talk about the units anymore, just m is 2. Okay, that's good. So what is K now? So what we know about K is that if V is 2, then the resistive force, which is kV squared, is equal to 48. Okay, so V is 2, K times 4 is 48, so we find that K is 12. Okay, so let's plug everything in. We have M2 A equals minus 2mg, which is minus 12. Don't forget, right? I mean, this is mg. This is the original weight. Okay, minus 12 plus k, what was k? K was also 12. 12v squared. Okay. Now, what is A? A is the double derivative of position, therefore the derivative of velocity. So our equation, and we can divide by 2. So A is v prime. Okay, I'm using that. So v prime is equal to, we can put out the 12 and then divide by 2. That's the 6 v squared minus 1. Okay, so this is a simple separated variables. So these are separated variables. It's not a linear one, by the way, right? Because of the square here. But it is separated variables. So we do that. So we get dv over v squared minus 1 is dt. 6 times dt. The t is the variable here. And so I bring all the v's to the one side and all the t's, which are not there, to the other side. And then I integrate. So now we have to integrate v squared minus 1. So we need a partial fraction of that, v squared minus 1, that is a times v minus 1 plus b over v plus 1. And we can use this now, calculate this very easily using Heaviside, right? V squared minus 1, oh, sorry. Of course we have to, sorry. I perhaps went a bit fast, but I hope everybody saw that the factorization of v squared minus 1 is v minus 1 times v plus 1, right? Okay, so we have v minus 1, v plus 1. We evaluate this for A, we have to evaluate it at 1, but of course then we have to calculate this one and we get 1/2. And for B, and by the way, perhaps by now you have figured out that it's always going to be the negative of the previous one, right? It's a negative 1. So we get this one cancels and we get minus 1/2. So we get 1/2. 1 over v minus 1 minus 1 over b plus 1. Okay. So that was an intermediate calculation. We now find that this, therefore, is and the derivative of this is 1/2 ln v minus 1 minus ln v plus 1, and that is equal to 6t and plus a constant. Yeah, let's take the constant here because we're looking for the general solution right away. For separated variables, we do that right away because it's not homogeneous, it's not linear, so we cannot use this trick of homogeneous plus particular. Okay, it's always better to bring these constants here to the other side, so we get, and then combine the ln's. That the combining the ln is this way, right? Well, absolute value or not, it doesn't really matter here. Remember, with the minus sign, it goes in the denominator, and so the 2 becomes a 12t plus 2c, but I'm going to rename c. So there's put it between quotes, a new c. And then we want to make it explicit, right? We need an explicit equation, so we're going to exponentiate. We get v minus 1 of v plus 1 is equal to e to the 12t plus the c, which is e to the c times e to the 12t, so we can write this as a times e to the 12t. That's our, so we have, let me write it up here, this is our solution, albeit not, it's still in implicit form. We should solve for v, so solve for v. Although at this point, we can perhaps use the calculate A. It's sometimes easier because from now on we're not going to do any changes anymore. This is the solution. We just rewrite it in explicit form. So the A is always, the constant will be the same all the time. So let's calculate it now. So before I do this, therefore, I'm going to do the calculation of the constant. So initial condition. So we were at the launch of the V0. What was V0 was 0.6, so 6/10. Okay, so let's plug that in. So we get 6/10 minus 1 over 6/10 plus 1 is equal to A, t equals 0, right? So that the exponential is gone. So this multiply everything with 10, so get 6 minus 10 over 6 plus 10 is A. Top and bottom with 10, right? So we get minus 4 over 16 is A, so we see that A is minus 1/4. Okay, so A is minus 1/4, so we get V minus 1, V plus 1 equals minus 1/4 e to the 12t. Okay, so now we can solve for V, right? So V minus 1 is, although, look, I calculated A, but perhaps it's better, this is just aesthetics or being neat, is I know A, but let's read, because it's a fraction with a negative sign, it's going to confuse me, so I'm going to use A again when I find the solve for V, the explicit equation. V minus 1 is V plus 1 times A times E12t, and that is equal to V A E12t plus A E12t, and that is V minus 1. So the V terms come this side. V minus V A E12t is equal to 1 plus A E12t. So V 1 minus A E12t is equal to 1 plus A E12t, and therefore V is equal to 1 plus. And now let's plug in what A is. A is minus 1/4. So 1 minus 1/4 E12t divided by 1 minus minus plus 1/4 E12t. Okay? And notice that there's a terminal velocity here that would be 1 if you take the limit for t going to infinity. I could ask that, right? So the limit for t going to infinity of v is 1 here. Okay, the resistance is such that it prevents somehow this object from falling too much. The air resistance is keeping it up, right? It is kind of floating almost, okay. Okay, so that's an example of, yeah, by the way, I said this very quickly, but I hope this is clear. This is clearer if you write it, which one often does, is by multiplying top and bottom by e to the minus 12t. So multiply top and bottom with e to minus 12t. Of course, every term. Then you get e to the, oh no, yes, sorry, it's minus 1. Sorry. Let's do it. Sorry, I jumped the gun here. Let's calculate it. Sorry. So let's do the calculation I said. So with e minus 12t. So e minus 12t minus 1/4 over e minus 12t plus 1/4. That's the result of what I just said. Okay. Now, if I now plug in infinity, so the limit for t going to infinity of v. Well, that is, since this is a negative power, this is 0. So get minus 1/4 over 0 plus 1/4, which is negative 1. I'm sorry, it was negative 1. I was a bit surprised that it would float. No, it's going to come down eventually with this kind of velocity, 1 meter, minus 1 meter per second, that it falls down. So, okay. Right, so yeah, so I showed here that it's very rash to try to figure out what the limit is without doing the calculation, and that's when I made my mistake. So always do the calculation, and then you see exactly what the limit velocity is. Okay, so that's motion. Now, segueing into the harmonics, What we actually never looked at is, let's look at this same problem here, a similar problem here. Suppose we have an object, so we are now on Earth, so this is on Earth again, and we're gonna, and this is like in a liquid, so this is in a vat of, this is a liquid here, and we're launching again a rocket. Let's see, what are my data here? Yeah. Okay, sorry. So now I have an initial position. So this is at 3. I'm at this height. So the vat is, let's say the liquid is at the bottom. That's in the bottom of the ocean, and I'm launching now whatever submarine or something like that, and it's at this position, and I'm launched it with a speed of 6. So 6 feet per second square, 6 feet per second. I'm launching it. Okay. So its weight, the weight of this little submarine or whatever it is sorry, we had 96 pounds. And suppose that the resistance is proportional to the height or depth, the height, let's call it the height. And such that at the moment of launch, okay, the resisting force F resistance was equal to was equal to 36 pounds. Okay, so this is not something we have seen, but I just want to show you that this is actually something we can solve as well. What is different here? The difference is that the resistance is not proportional to velocity, but to position. So the higher up in the liquid you are, the less resistance or whatever you have. So that what this means is that this resisting force is proportional to y. So we will have a y in here, not just v. That makes it different, okay? So remember, our equation is still ma equals minus mg plus the resisting force. So in this case, m will be the double derivative, is minus mg plus ky. So what we get is, instead of a first order equation in v, a second order equation in y. We noticed, we remarked this in that chapter 4, that this actually is what in general happens, but we didn't cover that because we hadn't done second order equations yet. But now we did second order equations, so we can actually look at this problem. Okay, so let's solve this problem now. So we have our equation of this, of the motion of this guy. So the couple of things we have to find. What is m? So we know that the weight 96 is the weight, and therefore is mg, that is 32m. So we see that m is 96 divided by 32, which is 3. Okay, so the mass is 3. What else about k? At the moment of launch, so what is y then? At the moment of launch, remember, y is 3 then, because this is the moment that we launch at, at this height. So y is 3. If y is 3, then f is 36. So 36 is 3 times k, and therefore we see that k is 12. So be careful, it's not the velocity, it's not the 6 that we have to plug in, it's the 3, the position. Okay, because it's proportional to position, not to velocity in this case. This is not a realistic model, by the way, you'll see why. But I mean, in theory, this is possible. Theoretically, you could have some kind of weird liquid that has this property, but okay. So this is where we are. So let's write down our equation. So m was 3, right? So 3y double prime equals minus mg. But mg is just the weight, so that's minus 36 plus 12y. Sorry. You have to be very careful here. My resisting force is going to be negative. I should have said that. So I'm going to kind of just declare that here. So I'm going to have here k is negative 12 here. The resistance is proportional to the not to the height, to the depth. That's what I meant to say. I said it, but then I changed it. So in other words, the deeper they are, the more the resistance is. That's what we kind of would expect, that the liquid gets denser and denser, let's say, okay? So so I should make this clear. In this case, so the equation is therefore here, minus ky. So here it also should write it as a resisting force as a negative. Okay, so I'm saying, follow just what I was doing here. So this is minus 12y. As I said, it's not very realistic, so I'm not going to pay too much attention to the actual physics of what is happening here. So this is what we have. So right. Right. Okay, so what is this now? Okay, so this becomes this is now a second order linear, but even constant coefficient. So let's write it like that: 3y prime plus 12y equals minus 36. So it's with constant coefficients, and we know how to solve this. In fact, this is exactly also what the equations for harmonic motion, in case of a spring, this would be what? The motion of a spring without damping, right? There is no y prime here. So that's what this will model, because the differential equation is the same, the behavior will be the same. Now we kind of know what happens to springs that have no dampening. They go up and down, they keep jumping, right? They keep oscillating. Well, let's see. So first of all, we divide by 3 here, so we get 4y equals minus 12. Okay, so step 1, the homogeneous, or whatever step, but I mean solving it now. We do the complementary homogeneous. So this would mean that y double prime plus 4y equals 0. So the characteristic equation, it's a constant coefficient, so we can do that, is t squared plus 4 equals 0. So we find that t is plus or minus 2i. I hope you see me that complex conjugates, right? So we know that the homogeneous solution will be a times cosine 2t plus b times sine 2t. Okay, because that's how the general solution of a homogeneous linear equation with constant coefficients looks like if the roots are complex. Okay, so step 2, now we need to what do we need to do? Well, we know that our solution is going to be of the form, this is a polynomial, and so we know that the particular solution will be of the form, a general polynomial of the same degree, a, so just an a constant here, that's the only thing that we have, the degree 0 is a constant. Now, if the y term would have disappeared, then we would have to multiply with a t, but it's not the case, so it is really just that. And of course, it's very quickly to see, because y prime and y double prime are both 0 in that case, so we get 4y equals minus 12, so we plug this in here, right? So we see that a is minus 3. Okay, so our solution is, so this is a new a, right? It's not the a of the homogeneous. So in our case, the solution is minus 3. The particular solution is negative 3. So what is the general solution is minus 3 plus a cosine 2t plus b sine 2t. So this is our general solution. Now we still need to do the initial condition. So what is also different in this problem than in mechanical, as I said, is not only that, in the previous case we were given an initial velocity here, right? Launched with an initial speed. Here we have to have more information. We have the initial position and the initial velocity. So this means that y is at t equals 0, y is 3. So t equals 0, y is 3, and the velocity is 6, it goes up. Okay, so let's put this in. So 3 is equal to minus 3 plus a, right? Because right, the sign disappears. I'm plugging this in here in this equation, right? So I see that a is 6, and then I take derivative. Y prime is equal to minus 3 plus 2, no, minus 2 a sine 2t. Derivative of sine is minus cosine. Derivative of cosine is minus sine plus 2b cosine 2t. And now I plug in these two values, and I get 6 is equal to minus 3 plus 2b. So I see that no, okay, I thought that I might have copied it from my notes wrong. I thought it was but it doesn't matter really. So we get 9 is equal to 2b. We see that b is equal to 9 halves. Okay, the fraction is not a big deal, right? So our solution is y is equal to minus 3 plus 6 cosine 2t. Boom, 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 boom. I have the feeling that I used the wrong value somewhere. 30. Wait, where did I get the 36 from? The weight was 96. Why did I write 36? The weight was 96. I'm sorry. Weight is 96. 96. So this was 32. I'm sorry about that. I knew it was the number was not entirely correctly. Minus 32, right? The weight was 96 here, right? So mg was 96, not 36. I don't know. I copied that wrong. So if I divide by here I divide everything by 3, so I get the next one. So the constant here is not. It's minus 32, and so minus 32. So a is minus 8. Okay, that's more like it. So we get here a is minus 8. So this is minus 8. So we get a minus 8 here. So we see that b is 8. Right? This, where did I get this from? No, sorry. Where did I plug in my... here, this equation. Sorry, here. In this equation, 8, so a is 11. Sorry, I said that wrong. Yeah, a is 11. And then here we have also 11 minus 8, so we get 6 minus 8 is b, so b is 14 equals to b, so b is equal to 7. Oops. And I feel it is a minus sign that I've forgotten. Sorry, I'm messing up a little bit here. A is minus 8. A is 11, right? And then B, sorry, did I? No, that's correct. B is 17. Okay, sorry. Yeah, I got it right. So this is now, therefore, the motion is, so this is A is 11, is 11 cosine 2t plus 17 sine 2t. Oh, minus 8, sorry, minus 8. So a little bit strange here, that but what is happening here is that this, okay, we launch it, but it actually will go down up to minus 8 here, and there it will start. This 11 and 17 sine 2, we know what this means, right? This is an oscillatory behavior, and so so with frequency 2. So so in this system, what happens is kind of a weird thing, is that this object will sink from its initial position 3, where was it? Initial position 3 to minus 8, so somewhere here. So I'm assuming that this goes down, right? Okay, I got my axis, okay. Assuming that we have more to go down here too. So it will go somewhere here, and then it will go fluctuate around there, okay? Which I find a little bit strange, I must say. So I'm kind of wondering whether I put my numbers incorrectly, but I got this This is what I got anyway. Okay, so this is just to show that when you're dealing with mechanics, well, whereas we saw it as application of first order, it is actually also as application of second order. Okay, but I'm just wanted to say this. This is not. I'm not going to ask you to do this because we haven't really covered this. I just wanted to show you. But in the meantime, I solved an equation, and that's what it means. All come down to everything is always these applications have this extra complication that you have to find the differential equation. And then once you have the differential equation, you solve it. So there's two steps, and that the first step to find the differential equation could be the one where you get stuck, and that's kind of a pity because if you don't have an equation, you cannot solve it. So make sure that you at least have at most as much as you can of this equation, that you can do at least some stuff. So I want to do the last thing in this review is an RLC circuit, and I'm going to keep it very simple. I'm just going to give the various values. So remember, the equation is LQ double prime plus RQ prime plus 1CQ is 0, where Q is the charge. Okay, but in these kind of problems, we want, so the question is this. So we have L is 2 henries, say, R is 10 ohm, Q is 1/12 Faraday. Farad comes from Faraday, but I don't know why I've abbreviated it. The initial, so Q0, the initial charge is 0 Coulomb, and the initial current is 1 ampere. Okay, so these are the data, and this is our equation. So what is the current at any given time t? Okay, remember current is I, so that's one extra thing that you have to do in these RLC circuits. But let's solve it. Okay, so L is 2Q double prime plus R is 10Q prime plus 1/12. The reciprocal of 1/12 is 12. 12Q equals 0. So that is Q double prime plus 5Q prime plus 6Q equals 0. That's homogeneous, so we do the characteristic equation. Oh no, sorry. It's not supposed to be, sorry, I didn't give you the full question. And a battery provides a charge of, 3 e to the minus 3t Coulomb. Okay, so this was the without the charge, but now with the charge, of course, this comes here, right? That's the forcing function. It's forced. Here you see a bit why it's called force, because we're forcing some energy inside, or some electricity that we bring into that circuit. Okay. So, right. So this is the complementary homogeneous then. Oh no, sorry. This was supposed to be 6. This is 6 here. So let me write down the equation before. So here we would have 6 e to the minus 3t, and we divided now everything by 2. Then it's 3 e minus 3t. Sorry. Let's not go too fast here. Okay. Why is it working? No, I lost that one. Okay, so let's do the complementary homogeneous. The complementary homogeneous, Q double prime plus 5Q prime plus 6Q equals 0. So the characteristic equation, t squared plus 5t plus 6 is 0. By the way, don't just watch this thing and say, oh, okay. Stop, solve the problem on your own, and then come back to the video and check whether your answer is correct. This is how you do reviews. I mean, I'm saying it a bit, I've said this several times, but I should have said this perhaps in the beginning of all the reviews here. Do this that way, right? Because that's the best way to see whether what you figured out and what you make mistake. Because then, see, this is the best thing to do, is for you to try And if it's correct, great. If it's not correct, then you can see, okay, where did I miss? And how do I make sure that the next time I don't miss there, don't go wrong there? Okay, of course, calculation errors, typos, things, that's nothing you can do about that, except for being very, very careful. Okay, here we go. So this one we have to factor, and of course everybody knows how to factor this. So we have two roots, t is -2 and t is -3. Great. So we know that our homogeneous solution will be a e to the -2t plus b e to the -3t. Right, these are the roots, real roots, and these are the coefficients in front of the power of e. Okay, so that's that. And now the particular solution. So what we are dealing with is a polynomial times an exponential. And so here the alpha, so alpha is -3 here, and we know what we're going to do is a variation of parameters using this alpha. But, and this is already something to notice, this is also a root of this equation. So we know what is going to happen. We know that the u term will disappear. U term has to disappear. This is a check for, this is good to know that it's going to happen, because if it doesn't, then we know we made a mistake. Okay, let's see. So we need y prime, that is u prime e minus 3t minus 3u e minus 3t. Y double prime is u double prime e minus 3t minus 3u prime e minus 3t minus 3u prime e minus 3t plus 9u e minus 3t. I hope everybody knows how this goes, right? Now I plugged, and that's right, y, and of course I should have written q. Okay, so I plug this in, I get, we know that the e minus 3t comes out. We have q prime. Q double prime, so get a u double prime, these two terms is -6u prime, and we have a plus 9u. That's the contribution of q double prime. Now from q prime we have 5 times these two terms, so plus 5u prime minus 15u, and then we have the 6 times q, which is just 6 times u. And that should be equal to, what was it, 3e minus 3. 3e minus 3t. Great. The first thing that has to happen is because the variation of parameters tells us this has to go, because we want something without exponentials now. But the second thing that has to happen, because here, let's see, we have 9u plus 6u minus 15u. 9u plus 6u minus 15u. It does all cancel out. So our differential equation u double prime minus 6u prime plus 5u prime is minus u prime equals 3. Okay, that's our differential equation. So what does this tell us about the solution? So this is where now, so there is no u term. This has degree 0, so our general solution has a general polynomial degree 0, but because there's no u term, we have to multiply with t here. So that's how the general solution will look like, and then it's very easy to find. There's derivative and double derivative is 0, so if I'm plugging in, I get minus a is 3, so I see that a is -3. Okay, so let's put everything together. So u is -3t. Okay, so we have first of all here this solution, and but then don't forget u itself was introduced this way. So we find that q is -3t e to the -3t. Okay, and so now step 3, the general solution, we put them together. This is the particular solution, so -3t e to the -3t plus the a minus 2t plus b e minus 3t. That is q, right? That was the particular solution. Yeah, these two. Okay. Okie dokie. And now we have the initial conditions. If t is 0, then q was 0 and I was 1, I guess, right? What did I say? Yeah. Okay. Here. So plugging in, this is 0 is equal to, if I plug in 0 in the first term, that's 0. Here I get an a, and here I get a b. Okay. And now I have to take the derivative, so q prime, which is good because I need it anyway. I need the derivative. This is going to be the charge. So this derivative of -3t, that is -3 e to the -3t, derivative of the first factor. But there's a second factor, it's a product, so we get a plus 9t e to the -3t, plus the derivative of minus rather, 2a e minus 2t minus 3b e minus 3t. Okay, and so this was 1 if t is 0. In this term, the first term is minus 3, the second term because of the t is 0, and then we get a minus 2a minus 3b. So we see that, bring this to the other side, that 2a plus 3b is equal to negative 4, and a plus b is 0. So I'm going to do the substitution just to do something else. A is negative b, so I'll plug that in. I get 2 times negative b, I plug this in here, right? Plus 3 times b is negative 4, so that means that b is negative 4, and therefore a is 4, because of this, okay? So we see that our solution, now what is the solution? Well, actually this one. So I is equal to minus 3 e to the minus 3t, plus 9t e to the minus 3t, minus 8 e to the minus 2t, and minus plus 12 e to the minus 3t. I plugged it in correctly. Okay. Now we have two like terms here. These two are like terms, so we get a 9 here. Not that that is necessary to do, but I'm just saying. And then we have an e minus 3t. So if I plug out the e minus 3t, I get a minus 3 plus 12, that is a 9, and this is a 9t. So actually I could also factor out a 9. This is just cleaning up. Not necessary, but just saying, because sometimes you might have to do other things with such a thing, so it's always good to see how you can do that. Okay, so that's how this circuit will react, and we know that. So what happens, of course, that again, when t tends to infinity, well, all these terms go to 0, so the charge will dissipate. Okay, so after a very short time, in fact, the charge will have dissipated. Because that's no surprise, because there was no charge to begin with, and then the battery was almost depleted, right? Because I mean, look at this battery here. This is not giving much, right? Because of the negative t, it's an exponential decay, so the battery was decaying like hell. Okay. That's the physical interpretation, which is something I don't care about in the questions, but of course its physical interpretation is sometimes important to find out whether the sign, all these little details do matter sometimes, okay? But as far as the units are so concerned, yeah, also be careful that everything is in the same units, right? Especially with feet and inches and kilogram versus grams and something like that. I normally don't like to trick people, but sometimes the numbers are so weird that it's better to use a different unit, but okay. So that's the review for the applications, and I realize that these are the so-called word problems, but don't forget that differential equations is really about applying all these things to science and so this is really one of the main goals of differential equations. Some of you are going to do electrical engineering, so you're definitely going to see RLC circuits and all these things. So keep that in mind, that applications are important, and so you have to do not dismiss them. There will be at least 2 questions on these things on the quiz, on the final. Okay, all right.